We are in Chapter 1, Section 2, where we are discussing stress and axial loads. This is the second session in Section 2, and we look at components under normal stress only and components subjected to shear stress only. Here again is a glimpse of the overall scheme of things, and we are in Session 6. We earlier mentioned about normal stress and shear stress. Sections are taken perpendicular to the axis of the component subjected to various loads, and the variation of stresses are found out. The stresses in these perpendicular sections can be complicated when the loads are complex. They would comprise of both normal and shear stresses. Here we look at a simple case where a section perpendicular to the axis of the component is subjected to normal stress only. The component considered is a bar subjected to axial loads. The bar has uniform cross-section. So this is the bar considered. It has a force F acting on one end and attached to a ceiling on the other. We find the stresses at the point C on a section perpendicular to the axis of the bar. To start with, let us look at the forces acting. So there's a force F acting here, and for equilibrium, the ceiling will exert a force F acting on the opposite direction. EC will be in equilibrium due to a force F and another force F acting in the opposite direction due to VC. AC will be in equilibrium due to a force from the ceiling and due to a force due to BC. Perpendicular cross sections have been taken at different portions of these bars, and the variation of normal stress has been found out. It has been found out that near P, the variation of normal stress is non-uniform. This is because the force F acts near B. However, at a distance from B, such as C, the stress distribution in a perpendicular cross-section has been found to be uniform. So this is the uniform stresses acting at section C. Now consider small area within the section of del A, and let the force acting on that area be del F. Then the stress acting on the area is equal to limit del A tends to 0, del F divided by del A, which is equal to dF divided by dA. Now the stress in this perpendicular cross section is constant. So we can integrate both sides of this equation and we get sigma constant is equal to F divided by A. So the constant stress is given by the force F divided by the perpendicular cross-section area. The resultant of these stresses is the force F that passes through the axis. We earlier considered a bar subjected to a tensile force. We then took a cross-section perpendicular to the axis of the bar at a distance from where the force was acting. We discussed that the stresses acting on the cross-section would be uniform. We mentioned that the resultant of the stresses would align with the axis of the bar, which passes through the centroid of the section. Here we will show that if we have an arbitrary cross-section to which uniform stresses are applied, then the resultant of those stresses will pass through the centroid of that cross-section. This case is similar to the case of a plate of uniform thickness subjected to gravitational force. The resultant of the gravitational force acts through the centroid of the plate. So here we have an arbitrary cross-section. Let this cross-section be subjected to a constant stress sigma. Then this small area will be subjected to a force sigma dA. If F is the force acting on the whole cross-section, then F will be given as integration sigma dA. Let us now arbitrarily take two axes, an x and a y axis. Let us find moment about the x-axis. So the force acting on dA is sigma dA. It multiplied by the distance y would give the moment of the small force. We can take small areas throughout the cross-section and find the total moment. The total moment would be given as integration sigma y dA. Now let the resultant act at a distance y1 from the x-axis. Then the resultant will create the same moment. So Fy1 is equal to integration sigma y dA. Similarly, we can get the equation Fx1 is equal to integration sigma x dA. We can divide both these two equations by A. Then we get sigma x1 is equal to sigma integration x dA by A, and sigma y1 is equal to sigma integration y dA divided by A. Now these two equations are the formulas of centroid. Hence, we can say that the resultant acts through the centroid. We earlier discussed that structures can be subjected to complicated loading. Under such loading, the perpendicular cross-sections of members will be subjected to complicated variations of normal and shear stress. Such variations will be studied in later chapters. Earlier we looked at a straightforward case of only normal stress acting, and the normal stress was uniform across the cross-section. Here we look at a case where only shear stresses are acting. So this is a bracket attached to a wall on which a force P is acting. To start with, we'll look at the equilibrium of the whole bracket. So if there's a force P acting, there must be an equal and opposite force P due to the wall, as shown. As earlier mentioned, this force P is parallel to the cross-section CC. So it will create a shear stress on the cross-section CC. Now let us take a cross-section, a section at CC. Then the right-hand portion between BB and CC would be in equilibrium. So there would be a force V acting along CC. If we take the equilibrium of the left portion, then there will be a force V acting as well. These two forces V form an action-reaction pair. Now this force V would be formed of small shear stresses acting on the whole section CC. Unlike normal stresses, shear stresses are not uniform throughout the cross-section, but we use an average shear stress. So here tau average is equal to V divided by A, where A is the area of the section CC. Here we deal with shear and bearing stresses in bolted connection. We have discussed this case before of a pin bar subjected to a load P. We discussed action-reaction forces and there being two sets of action-reaction forces at A and B. Here we have two plates connected by a bolt and subjected to forces P on the left and the right side. We take a section AA and this is the corresponding diagram. Here we see a force P due to the plate onto the bolt. This is an action force. So the bolt will react with an reaction force onto the plate. This again is an action force. So the bolt would react the reaction force onto the plate. This is an equilibrium diagram of the bolt. Here only the action forces are shown. So the forces that act on the bolt are shown and not the forces that bolt exerts on the environment. If we take a section 1-1, then as earlier discussed, the average stress would be P divided by A, where A is the perpendicular cross-section area of the bolt. The reaction forces that act on the plate due to the bolt are shown here. The bolt will try to crush through the plate. So if the bolt can crush through this distance or this distance, then the joint will fail. The stress that the bolt exerts on the plate is called bearing stress. The variation of bearing stress is complicated, but the average bearing stress can be given by dividing the force by the projected area of the bolt on the plate. So the bearing stress is given as P divided by D into P. We note that the action forces cause shearing stress and the reaction forces here cause bearing stress. In the earlier slide, we looked at two plates connected by a bolt with forces applied to the plates. The plates caused a shear stress on the bolts, and the bolts in turn caused a bearing stress on the plates. The earlier case was a case of single shear. Here we have a case of double shear. So there are three plates, the top plate and the bottom plate pulled by a force P by 2 on the right, and the middle plate pulled by a force P. As earlier, we take a section A through the bolt, and this is the diagram that we get. P by 2 is a force by which the plate is pulling the bolt, and the bolt will have a reaction force on the plate. Here also the force is P, and the bolt also will have a reaction force on the plate the same magnitude. This is same as the top plate. So here we have only the action forces on the bolt, and the bolt is in equilibrium due to the action forces caused by the plates. So the force here is P by 2, and if we take a section 1,1 or section 2,2, we see that the maximum shear force that we'll have is P by 2. Here we see the reaction forces. So these are the forces that the bolt applies on the plate, on the three plates. So here the bolt applies a force of P by 2, which causes a bearing stress on the plate, and here in the middle plate the force is P. So on the top plate the bearing stress is P by 2 dt, while this bearing stress for the middle plate is P by dt. So the bearing stress the middle plate is higher. We look at an example here. This is a pin jointed structure subjected to load, and we are required to find the stresses in the members and in the pins. We have dealt with plain trusses and plain frames, and also we have learned about normal stresses and shear stresses in pins. So we will use that understanding here to find the stresses. The load applied here is 30 kilonewton, and these dimensions are given. So initially we look at the bar AB. This bar AB has a dimension of 30 millimeter by 50 millimeter. So the top plan view is 30 millimeter. For connection purposes, the bar forks out at B, to be here, and these forks are 20 millimeter by 50 millimeter. The bar BC has a has a diameter of 25 millimeter and is round shaped except at the ends. So at the end here, in plan view, the dimension is 25 millimeter, but the depth is 50 millimeter. Similarly here, in plan view is 25 millimeter, but the depth is 50 millimeter. So the bar is circular in the middle, it becomes rectangular at the ends. This figure gives the end view of B. So looking at B from this side, and it connects both AB and BC as well as a bracket for the 30 kilonewton load. So this part is due to BC. The shaded portions are due to the forks of AB, and this part are due to the bracket through which a 30 kilonewton load is suspended. The pins are all 20 millimeter in diameter. Here we see the pin at A. Now, if the force in AB is FAB, and then this is the forces that will act on the pin. So it will be subject to force FAB here and two forces FAB by 2 here. And this is the figure of pin C here, and it will be subjected to a force BC due to BC and two forces BC by 2 on the other side. This is the pin at B. This is more complicated than the other two. So this is this pin. So it is subjected to forces Fa by 2, and due to AB, Fa by 2 here is also subjected to force FBC, and the two parts of this bracket support a load of 15 kilonewton each. We initially find the forces in the members AB and BC. We then find the stresses in these members, and after that we look at the pins at A, C, and then B. Force applied at the joint B. Here we don't need to find the reactions at A and C. We can start this problem from the right. Thus, we look at the free body diagram of the joint B. The joint B is subjected to forces along AB and BC. We need the angle, so we've made with the horizontal. So tan theta is 75 by 150 or 0.5, from which we get theta as 26.6, and this angle we get as 45. So here FAB cos 26.6 plus FBC cos 45 is equal to 0. Solving the forces in the vertical direction, FAB sine 26.6 is equal to FBC cos 45 plus 30. From these two equations, we get FBC is equal to minus 28.3 and FAB is equal to 22.36. FBC is negative, so the force acts towards the joint B. These forces are the force that act on the joint. The joint in turn we'll have reaction forces that will act on the bars AB and BC. We see that the AB will be in tension and BC would be in compression. We now find the stresses in AB and BC. The cross-section area of AB is 30 multiplied by 50. So the force multiplied by the cross-section area gives a stress of 14.91 MPa. The middle portion of BC is circular, so we get the stress by dividing the force by the cross-section area, and we get it as minus 57.6 MPa. We now look at joint A. We have found out the force in AB, and the forces in bracket by equilibrium are 11.18 each. So the maximum shear force is 11.18 kilonewton. We divide it by the cross-sectional area of the pins, and we find that the stress in the bolt at A is 35.6 MPa. In turn, exerts a force on the bar AB. So the diameter of the pin is 20 and the T thickness of the bar is 30. So we get the bearing stress that acts on AB. We do not calculate the bearing stress that acts on the bracket at A. We now look at the connection at C. The force in BC is 28.3. It is compressive. So this is the direction of the force in the connection. Here again, the force in the two arms of the bracket is 14.15 kilonewton, and the maximum shear force that will act is 14.15 kilonewton. Divide that by the area and get the shear stress acting on the bolt C. The pin exerts a bearing stress on BC, and the force is 28.3 kilonewton. The diameter of the pin is 20 and the thickness of the plate is 25, in which we get stress of 56.67 MPa. As in the case of pin A, we do not calculate the bearing stress on the connection, on the bracket. Here we discuss the forces and stresses acting on the connection at B. So this is the diagram of the end B. These two shaded rectangles are due to AP. This rectangle in the middle is due to BC. And these two arms are of the bracket through which the load 13 kilonewton is suspended. So this is pin B, shown with all the forces acting. These two forces are due to the fork portion of AB. This force is due to BC. These two forces are due to the bracket through which the load is suspended. We notice that pin B is more complicated than single shear and double shear case we have dealt with till now. Here we have to take different sections and find out where the maximum shear force and thus the shear stress acts. We notice that if the truss is in XY plane, then P1, P2 is in the Z direction. Here we need to find the forces in section B between these two loads and section E between these two loads. We notice that the arrangement is symmetrical, so the shear force in section D will be the same as the shear force in section H, and the shear force in section E will be the same as the shear force in section G. So here we have taken a section at B between these two loads. There's an action-reaction force acting at D, and starting from the left, we see that the magnitude would be 15 kilonewton. Next, we take a section at E. This time, starting from the left, there are two loads. This will be 15 kilonewton and this load of 11.18 kilonewton. So we have to find out the action-reaction forces that acts at E. This diagram shows the portion of the pin left of the section at E. There are two forces acting on the pin apart from the force in the section E. This is the diagram of the forces looking from the end. We can see that we can find out the force Fe by resolving forces. So Fex is 11.182 cos this angle, which we get as 10 kilonewton. Similarly, we find out Fey, which also we get as 10 kilonewton. So the magnitude of Fe is equal to 14.14 kilonewton. Now this magnitude is less than the 15 kilonewton magnitude at point D. So the maximum stress in the pin is 15 kilonewton divided by the area, which we get as 47.75 MPa. It is to be noted that the pin is subjected to bending, but we haven't considered that. Also, the bearing stress in the clevis, which is at the end B, will be less than that of A, since the force is half in the clevis and the thickness has been reduced by 2/3. Also, we do not consider the strength of the bracket here.